Your Koomey regulators serve a variety of functions throughout the hydraulic system. They're located just about everywhere: in the pods, the operating panels, the control manifolds, the test panels, and the hose reels. Whatever their function, they all serve the same purpose: to regulate a high inlet pressure down to the usable functioning pressure of the equipment in use. The next few programs in the Subsea Maintenance and Repair series will detail repair procedures for AKRs, MKRs, and HKRs. But first, let's spend a few minutes just to tell you how they work. That's the purpose of this program. This ought to give you a better feel for the valves when you go about repairing them. The 1-inch HKR and MKR. You'll still find a lot of them out there, even though they're an older design. Actually, they were manufactured for Koomey by Gilmore when Koomey was a division of Stewart & Stevenson. Koomey separated from Stewart & Stevenson many years ago. Today, Koomey and N.L. Schaefer supply the replacement parts for these valves. In straight hydraulic systems, you'll find 1-inch MKRs in the pod test panel and in the acoustic mini-pod. The 1-inch HKRs are located in the pods to regulate pressures for the annulars, subsea manifold, and possibly fail-safe assist. Internally, the HKR and MKR operate identically. The only difference between the two is in the way the output pressure is controlled: hydraulic pilot versus a spring. Let's concentrate on the nuts and bolts, how the valve regulates. Keep in mind that this process is identical for both the MKR and the HKR. Let's look at this HKR valve in the full open position. Here we can show you the very simple flow path. System pressure enters the inlet, passes over the indentations, moves through the body cavity, and exits the outlet. The pilot-to-outlet pressure ratio in this HKR is 1:1. Quite simply, that means the regulated pressure out equals the hydraulic pilot pressure you apply. If pilot pressure equals 1500 psi, for instance, you'll get an outlet pressure of 1500 psi. Simple. Now, say this valve is actually regulating pressure to a component that functions at 1500 psi. Your pilot pressure should be 1500 psi. When pressure at the function drops below 1500 psi, the regulator operates. When the function is complete, the flow stops and pressure builds up. This increasing pressure has continuously been transmitted back to the valve. This back pressure opposes the pilot pressure being applied on the top of the plunger. It acts on the bottom of the plunger and other opposing areas. The seal container begins to move up. When the back pressure equals the pilot pressure, 1500 in this case, a hydraulic balance is achieved. When in balance, the seal rings move into position over the inlet. The 3000 psi inlet pressure is sealed off against the seal plate. In this balanced position, there's 1500 psi above the plunger, 1500 psi in the valve body, and 3000 psi inlet pressure blocked against the seal plate. No flow. The valve is closed. Let's look at what the seals are doing and why they're so important. At the seal rings, the edges of the seal rings themselves are actually sealing against the seal plate and around the inlet port. When the inlet is blocked, the O-rings and backup rings are keeping high-pressure inlet fluid from leaking past the seal rings into the valve body. High-pressure fluid inside the bores acts primarily on the spring side of the ring. This assists the compression spring in holding the metal-to-metal seal. But some pressure acts on the O-rings. The O-rings, in turn, press on the backup rings. The backup rings serve, of course, to keep from pinching the O-rings between the bore and the edge of the seal ring. Now, you can't see it with the naked eye, but these sealing edges are slightly beveled, with the edge to the outside. If you could look at the edge under the microscope, it might look something like this. This bevel is there to allow the seal container to shift at a lower pressure differential between pilot and internal body pressure. Let's explain. Think of this seal ring as a piston. Not only is spring force holding the seals against the plates, but so is inlet pressure acting on the spring side areas as well. The slight bevel allows a minute amount of inlet fluid pressure in behind the bevel. Acting from there, this pressure opposes and slightly reduces the total combined force of spring and fluid pressure acting on the spring side. So the overall pressure differential between pilot and regulated pressure required to shift the seal container is reduced. Now, if the edges were flat, all force would be in one direction. No fluid could help reduce that force, so it would take a greater pressure differential to make the seal container move up and down. Let's go back to the closed position. Now we'll show you what happens when the valve vents. The valve will vent whenever the internal body pressure is higher than the pilot pressure. This can happen if there's a reduction in the pilot pressure or if there's an increase in body pressure. Either of these conditions can happen through normal operation. In other cases, venting usually indicates trouble, a leak. We'll deal with valve troubleshooting at length later in the Koomey regulator series. That's why the valve vents. Let's talk about how it vents. First, trace the vent path. The internal fluid cavity is exposed to the vent path here at the top of the pilot valve housing. The vent path runs through the housing to the pilot valve seat. Then it runs out the pilot valve body to atmosphere or sea. When seated, the poppet blocks the vent path here. It's held there by the regulated pressure in the valve body. Obviously, the same pressure acts on both ends of the poppet, but the surface area at the head end is slightly larger than the surface area at the sealing tip. So the pressure over the greater surface area holds the poppet in place. Let's assume overpressure in the valve body. The higher pressure in the body cavity overcomes pilot pressure and forces the plunger and seal container even higher. The container rises high enough so that this cap screw lifts the poppet off the seat. The inlet remains blocked. The volume of fluid causing the overpressure is now allowed to pass through the vent system. The pressure inside the valve body starts to drop. As the pressure balances again, the seal container lowers enough to allow the poppet to reseat. The inlet is still blocked. The vent is blocked again also. The valve is closed, holding pressure to the function. If we move up the pilot line from this HKR, we'll find a half-inch AKR providing the pilot pressure. Let's look at that AKR and the half-inch MKR. They're identical internally. The MKRs are located in the hose reels to regulate manifold functions while running and retrieving the BOP stack. Let's begin with the valve in the full open position. The inlet is exposed to the body cavity and fluid flows around the seal container to exit the outlet port. Notice the dump port is still blocked. The compression springs are holding a seal against the seal plate and around the vent port. Back pressure in the valve acts underneath the plunger seal area and bottom of the seal container to push it up to the closed position. Notice the dump port is still blocked, but now so is the inlet port. The compression spring, assisted by inlet pressure inside the hydroseals, holds a seal against the seal plate and around the inlet port. Both the inlet and dump hydroseal edges are beveled in the same manner as the seal rings in the other valves we've seen. If an overpressure situation develops and pilot pressure is overcome, the seal container and hydroseals move out of the way to expose the body cavity to the dump port. Fluid vents to tank. The inlet remains blocked. Pilot pressure brings the valve back to the closed position when the pressure balance is reached. In the AKR, the air pilot to output pressure ratio is 30:1. Well, that's it. These valves aren't as difficult to understand as they seem. All regulators work on basically the same principle, even though there are many different designs. Let's use this 1.5-inch HKR as a further example. For many of you, this valve regulates function pressure instead of the poppet-style 1-inch valve. In the full open position, pilot pressure forces a seal container down, and fluid flows to the function. In the closed position, back pressure to the valve balances the seal container in a position that blocks any flow. Overpressure forces the seal container up into a position that exposes a vent port, and the excess pressure vents. One more time, and we'll be a little more specific. Supply pressure enters the bottom port, passes through the body cavity, and exits the outlet port. The vent port remains blocked. These two holes in the seal container are designed to allow easy fluid access to the other side of the body cavity. As back pressure reaches the valve, the fluid pressure begins acting on the seal container to balance the pilot pressure. The force begins acting on the bottom of the container, the large cutout in the side of the container, and the bottom of the plunger. As the pressures balance, the vent port is still blocked, but now so is the supply port. In this block position, pilot pressure and valve body pressure are equal. At the blocked inlet, supply pressure is acting inside of the inlet seal rings. They work exactly as those we've seen in the poppet-style valve. These spring washers hold the vent seals in place against the seal plate and around the vent port. Notice that the vent rings need to travel only slightly farther up for the body cavity to be exposed to vent. So let's detail an overpressure situation. The imbalance, greater pressure below the plunger, causes the seal container to move up, exposing the vent path and fluid cavity to the vent port. The fluid vents until the pressures are back in balance. The seal container slides back down again, and both the vent and inlet ports are blocked once more. Before we wrap it up, there's one routine operating procedure we need to tell you about. Many of you may already be doing this. Run each regulator through an acceptable range of output pressures at least once a month. If the seal rings remain in one position, under pressure, for an indefinite period of time, the seals may wear a definite pattern into the plates. Once they do that, the valve may never seal again at different pressure settings. So you see how they work. The programs that follow in this Koomey regulator series go into repair and troubleshooting.